Hey, Dr. Clark here, and in this preview video, we're going to look at section 1.2, initial value problems. Let's take a look. So first, I want to just recap what we had done last time with the dry ice model. We had a couple variables. T was time, m of t was the mass at time t, so m of t is the function we're interested in. And then k showed up as a constant. Now, what we would really call this is a parameter because it's part of the model itself. So you notice m prime equals negative km. M is your dependent variable, your function. In this case, t is time is our independent variable. And k shows up as a parameter in the model. Maybe it's related to some geometry or the temperature of the water, that kind of thing, but it's some constant that's part of the model itself. And then C shows up as a constant relating to the initial mass. So if you drop in 10 grams or 20 grams or 30 grams, that's kind of determining the C. So C doesn't show up in the model, it shows up in the solution, whereas K is part of the model. Okay, so that's the difference between a parameter and a constant. Parameters are sort of part of the model, whereas C is constants that pop out when you solve the problem. And we had two models, one where the rate of change of mass was proportional to the mass, and one where the rate of change of mass was proportional to the mass raised to the 2/3 power. This was the better model because it took, it made sense of geometry, surface area. We're really saying that mass, the change of mass is proportional to surface area, and then we went from surface area to mass by doing that sort of algebraic step. When we solved this problem, we got c e to the negative kt, and when we solved this one, we got negative kt plus c to the 3rd power. Well, we actually didn't solve this one, but this is what the answer turns out to be, and we'll learn how to solve problems like that later on. And so this is, keep this in mind. Now, what we're doing today is something called an initial value problem. And an initial value problem, we're going to do something like specify the initial value of the function. So that dry ice had a certain mass to it, say 12 grams or 20 grams or whatever it was. Well, in this one, that C would just equal that initial constant, 20 grams or whatever. Here, it's a little bit trickier. If t is equal to 0, then you would get c cubed should equal the initial mass, and so c will end up being the cube root of the initial mass. But in some sense, the c is creating that initial mass. It's not equal to the initial mass, but it's determined by the initial mass. So the c takes on the same role when you plug in t equals 0, you just get c, and here you plug in t equals 0, you get c cubed, and so c is the cube root of initial mass. And that's what we mean by an initial value problem, where we have a differential equation here, and we specify the initial value, or the initial mass in this case, but in any problem we call it an initial value problem. All right, and the reason we want to do that is, for example, if you have something like dy dt equals 2y, well, e to the 2t is a solution, but 3e to the 2t is also a solution. Right? So differential equations have more than one solution, but for an initial value problem, well, when you plug in t equals 0, this one would get 1 and this one would get 3. So if you specified the initial value of the function, only one of those could be true. And generally speaking, for an initial value problem, it will end up specifying exactly one answer. So what do we mean by initial value problem? It's a differential equation together with a set of prescribed initial conditions at some particular value t naught. Oftentimes we set t naught to be 0, but it doesn't have to be 0. And for an nth order differential equation, we need to specify not only the values of the function y, but also its derivatives up to the n-1 derivative. So here's a nice example. This is a 2nd order differential equation. So we would specify the initial position and the initial velocity. Okay, if it was a 3rd order, then you would specify initial position, initial velocity, and an initial acceleration. Okay, so that's what an initial value problem, how that works. All right, and just a quick geometric interpretation, and I sort of alluded to this already. When you have a 1st order differential equation, and this was the mass problem, m prime equals km, that's that dry ice problem, we only had to say how much dry ice did we drop into the bucket. That was a 1st order problem, so you you specify the initial mass. A second order problem, you may have to specify the initial position and the initial velocity. So if you throw a ball off a cliff, you need to know how high the cliff is and also what speed the ball is going at if you're going to predict its trajectory. So that would be a second order problem. You're going to have to specify initial position and velocity. Things can get more complicated. For a third order, you'd have position, velocity, and acceleration, and et cetera, et cetera, et cetera. So geometrically, there's a whole bunch of possible solutions to a differential equation, but when you specify the initial position, then you're locking into one particular solution. For a second order, you'd have to not only specify the initial position, but also the initial velocity. So you might have multiple curves going through that point right there with different slopes, and then once you lock in the slope and the point, that locks in a solution. So that's kind of an idea of first and second order. All right, so that's the basic introduction to initial value problems. When we get to class, we'll do a bunch more, and we'll see some examples and learn how to solve them. But this at least tells you what we're talking about and connects it back to the dry ice.